So Shmuel is head of our quantum design team, our hardware team. My name is Sheir. I'm the team lead in quantum applications and algorithms at Qarakal. I have to say that my entry into quantum computing is weird, even by quantum computing standards. I didn't necessarily come from academia. My journey started over 10 years ago. In 2014, I started working at D-Wave in Canada. I worked there in the hardware team for a few years. I moved on to algorithms, applications. I moved to Volkswagen in Germany, and I led the quantum applications and algorithms research team there for 5 years. And about 2 years ago, I moved to Israel to join Qarakal, the Israel's largest superconducting qubits company. There's one thing that is kind of a theme in all these talks and in my experience in quantum computing. We all talk about scaling, and one thing that we don't really address enough is that bigger is not always the solution to quantum computing. We all want more qubits. We all want bigger problems. We all want to solve things that are bigger and greater. The problem with that is that we don't always stop and think, what are the implications of this? How do the increasing sizes of these quantum processors affect us in our ability to solve complicated problems? Well, that's really the thing that we're trying to solve at Qarakal. We're not thinking of just building one chip bigger and bigger and bigger. We're trying to think at the system architecture level. How do you actually build a quantum computer? One of the main problems in building bigger quantum processors is the scaling issues. You run into noise problems, crosstalk, control issues, timing issues, synchronizability. These are all very, very obvious scaling issues that you encounter when you just build bigger and bigger arrays of qubits. Well, one of the unique things about superconducting qubits is that, as opposed to all the other technologies that you use to make quantum computers with, we have a very unique privilege that our qubits don't actually exist in nature. We're the ones that have to manufacture them. We make decisions, we plan, we take these macroscopic loops of metal and we force them to become qubits. We have to make them do what we want. And this gives us a very unique freedom where we can actually choose how we want our qubits to behave. We can make big fat qubits that live a really long time and kind of work slow. We can make small qubits that are really fast, connected to a lot of other qubits. We can actually make a lot of very general design choices in how we want to build our quantum computers. Traditionally, in quantum computing, you kind of work in a very linear workflow. You have your qubits that sit on your chip. You have to build a compiler for them. You have to synchronize them and control them in real time. And then on top of that, you kind of lalbish an algorithm on top of it. And you have to make it all work somehow within the confines of your qubit array choice. What we believe at Qarakal is that you can actually do the opposite transformation. You can look at your algorithms, you can look at your fabrication techniques, you can look at at the way you measure and operate your qubits, and you can build a quantum computer that actually solves the problems that you want them to solve in the way that you can control and optimize. In this way, you can actually control the scaling of the way your quantum computer operates. We can start thinking in terms of computers, not in terms of individual chips. So here's an example of one of the quantum computers that we built, and maybe some people have had a chance to touch. This is a 20-qubit chip that we have sitting in our lab in Jerusalem. It's a tunable coupler technology. It's very similar to some of the computers built by Google, Rigetti, IBM. And one of the things that is very unique about this chip is that we designed it very specifically to solve certain classes of problems. We looked at industry use case problems that our customers were having, and we built this chip to actually solve these problems better than other chips. We've shown that we can actually calibrate, control, operate these qubits pretty much among the best in class in superconducting quantum technologies. And our goal is to try to scale this up to much larger scale quantum computers, to go beyond the single qubit, 2-qubit rates to tens of qubits, and eventually thousands and millions of qubits one day. Here's a few results from the last time we brought up the chip. These are a little bit outdated, but we've actually been able to solve a very specific industry use case from one of our partners, and this nice little peak here on the side is exactly what we were looking for. So basically, we've demonstrated this full stack end-to-end approach of designing a quantum computer specifically for targeted applications, and we've shown that we can scale and build computers at the system architecture level. Our roadmap is ambitious, but we really think that we've been able to tackle the major scalability issues in building quantum computers. Last year, or the past couple of years, we've been building our prototypes, our MVPs, demonstrating that we have the ability to design individual qubits, design chips, put them together in our lab, operate them, calibrate them. This year, we're designing our first special purpose error-corrected quantum computer. And our goal is eventually to scale to a full system architecture that we can actually place on-prem, operate any kind of algorithm in a modular way, and finally bring in quantum computing at the system scale. And yeah, we want this is basically what we want our quantum computers to be. True scalable quantum computers and not just individual chips. In order to think about commercial applications, we have to think about how commercial computing in general is used today. So if you have any more questions, feel free to come and find me, and thanks again.